So this is the first of a series of little videos that I'll be uploading. Okay, so I'll try to make them seem as natural as possible, as close as possible to the classroom spirit. So I'll be doing them with as little preparation as possible. Okay, so this first video, the idea is to introduce so-called ordinary differential equations. Okay, so for example, I'll give you some examples of ordinary differential equations and what do I mean by the word ordering over here. So differential equation is just an equation which involves derivatives, and the thing that you actually need to find, the quantity that you need to find, is trapped inside a derivative. Okay, so that's what we mean by differential equation. Ordering just means that there are no partial derivatives, so you're largely dealing with functions of a single variable. Okay, so the derivative is the thing that you want to find is trapped inside an ordering derivative, not a partial derivative. If it's trapped inside a partial derivative, then you are dealing with partial differential equations. Okay, but those we learn to solve later on once we know how to solve these relatively simpler ordering differential equations. Okay, so examples in which these ordering differential equations pop up are essentially there are many of those. So the simplest one is that you have all seen is probably Newton's second law. So Newton's second law, for example, you can write down that the force acting on an object, the net force acting on an object, is equal to the mass of that object times the acceleration of that object. And I can also write this down as since the acceleration is a double derivative of the position vector, the force acting on object is equal to the mass of the object. This is the force, this is the mass, times the acceleration of the object. The thing that you usually want, the position vector, is trapped inside a double derivative. Okay, and the force you may know as a function of time or of position. Okay, so you need to solve this differential equation. Okay, so technically I should say that this should be a function of this r. Okay. You also have examples from heat transfer. So if you have a box, okay, and there's some temperature on one side, there's another temperature on the other side, there's some cross section area A. You know that if T1 is bigger than T0, then there's going to be some heat transfer that way. Okay, the rate at which heat is transferred is proportional to the cross section area A. It's also proportional to the temperature gradient. Okay, and since it's proportional, these two, you convert this into the equation by putting in a proportionality constant K. Okay, so this is the cross section area, this is the temperature gradient, this is the proportionality constant. To find out Q, the heat transferred, okay, you can solve this differential equation. Okay. You also have examples in form circuits. So for example, if you have an AC source which you connect to a resistor, and then a capacitor, and then an inductor. Okay, so this is a RLC circuit. You have some AC source V. You can apply Kirchhoff's second law. V will be equal to the potential drop across the resistor, IR, Ohm's law. Okay, then the potential across the capacitor, okay, Q over C, and then the potential across the inductor, where L is the inductance. Okay, and you can see, if you can find out the current, you can find out all the other quantities, and the current is trapped inside this derivative. It also occurs over here. Okay, so anyway, so the idea is that you need to get familiar with how to solve different kinds of differential equations, okay, ordering differential equations. Okay, and since these pop up all over the place. Okay, so first some terminology. So I'm going to be talking about the order of your differential equation. Okay, so the order just means that the order of the highest derivative that occurs in your differential equation. So for example, Newton's second law is a second order differential equation for the position vector, because the highest derivative that occurs over here is a second order derivative. Okay, the law of radioactive decay, where n is your number of radioactive nuclei. Okay, lambda is your decay constant. This is a first order differential equation because you only see a first order derivative over here. Okay. Now from now on I'll be talking about differential equations in general terms. So I'll be dealing with equations. For example, I'll be talking about in terms of x, which is your independent variable. Okay. And your y is your dependent variable. So y is the quantity that is stuck inside the derivative that you actually need to find. Okay. So you are talking then in terms of a differential equation will contain things like dy by dx, d2 y by dx2, and of course it can also include functions of x and functions of y. Okay. And of course also higher order derivatives. Okay. So for example, in this equation, the role of y is being played by n, the role of x is being played by t, and so on. Okay, so I'll be talking about in terms of general setting in terms of x and y. Okay, x and y physically could be anything. I'll also be focusing largely on so-called linear differential equations because these are the nicest differential equations mathematically, and these are also the equations that appear most commonly in applications. Okay, so a linear differential equation, let me just write how you can define a so-called linear differential equation. So what we mean by the linear differential equation is an equation of this form. So you have a naught y plus a1 y prime plus a2 y double prime plus dot 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 all the way to an y prime n is equal to p. So that we explain this. Okay, a naught, a1, a naught, a1, a2 all the way to an. These are functions of x and x only. They don't contain any y. Okay, they can be constants. Okay, b is also a function of x. It can be a constant but not a function of y. Okay, the prime denotes a derivative. So by this I mean dy by dx. 2 primes mean a double derivative. Okay, this notation over here means of course that you're taking the nth order derivative, so this means dn. Okay, fine. So for example, the equation for simple harmonic motion. Okay, so if you have a wall, you attach to that a spring and then you have a block, you pull the block and let it go, then you know the equation of motion for this block can be written as the mass times the acceleration of this block. This is will be equal to the force acting on the object, which is just by Hooke's law minus kx, where k is the spring constant. You can write this down in the form this form, of course, and then you can say that okay, the role of y is being played by x over here, the role of x is being played by t over here, and you can immediately see that this equation is a linear differential equation. The over here you have a2 is equal to m. Okay, a naught is equal to k. Okay, a1 is equal to 0, all the other a's are equal to 0, and b is also equal to 0. Okay, the nice thing about linear differential equations is that first of all they are nice to solve, they are relatively easy to solve. Okay, there's some special powerful theorems about them which we'll learn about as we go on. Okay, but the most important point is that loosely speaking the solutions obey the principle of superposition. If you find one solution, you find another solution, that the sum of those two the sum of those two solutions will probably also be a solution. Okay, but we have to be little bit careful about that, as we'll see. Okay. Okay, so now let me talk about first order ordering differential equations. Okay, first order differential equations. Okay, so these are the simplest equations that you can possibly talk about when it comes to differential equations. So first of all, I'll be talking about equations of the following type. Okay, so the first order derivative is equal to some function of x and x only multiplied by some function of y and y only. These f and g could be any function whatsoever, okay, but f is only a function of x and g is only a function of y. Okay, so such a differential equation, if you can put your differential equation, first order differential equation, into such a form, this differential equation can be solved by so-called separation of variables. Okay, so essentially what you have is that you take all the quantities that contain x to one side and all the quantities that contain y to the other side, and you just add up both sides. So let's do that. You can rearrange the above equation into the form that f of x times dx is equal to d of y over g of y, and then you can add up both sides. You get f of x dx is equal to integral of dy over d of y. Both of these integrals, of course, give you one constant, okay, but those two constants can be combined into a single constant, okay, and that's exactly what you expect from first order differential equation, that it contains one constant. Okay, so first order differential equations, they contain a constant whose value is fixed by the so-called initial conditions or the boundary conditions, so to speak. Okay, so the one prototypical example of such a differential equation would be the population decay model. So if you're looking at a sample of some radioactive material, the number of radioactive nuclei falls down in time. The rate is proportional to the number of nuclei present at that time. Okay, so lambda is the proportionality constant, is called the decay constant. Okay, if you want to solve this differential equation, what you then do is that, okay, you have this differential equation, you then just have separation of variables. So you, n, remember, is a function of time. Okay, so you take all the n to one side, all the time to the other side. Lambda is a constant. Okay, so this implies that I can write dn over n is equal to minus lambda dd, and then I can integrate both sides. The left hand side, the integral of the left hand side, of course, gives me ln n, and the integral on the right hand side gives me lambda dt, and I can also write down a constant plus c. Okay, so just for convenience, instead of writing the constant as c, I'll write ln c. Okay, so I can then rearrange this equation into the form I can take this, when I integrate both sides, I will get, instead of dt, I'll get t. Okay, so I'll take this ln c to the other side, and I can rearrange this as ln, and then I can exponentiate both sides to get and then I have n is equal to c e raised to power minus lambda t. Okay, so to determine the value of c, I can set t equal to 0. Okay, at t is equal to 0, the number of radioactive nuclei is equal to some initial value, which I can say n naught. Okay, so n naught will be equal to c times e raised to power 0, which is c. So c is nothing but the initial number of radioactive nuclei. So that's exactly what we expect. The number of radioactive nuclei falls down exponentially with time. Okay, so let me talk about another example. Okay, so here's a differential equation, dy by dx, nice first order differential equation, and this is equal to square root of 1 minus y square. Okay, you can solve this by separation of variables, okay, because the right hand side is only a function of y. Okay, so you can bring all the y to one side and all the x to the other side. Okay, but the first thing to note is that this is not a linear equation, so this is a non-linear differential equation. Okay, but anyway, we can still solve this differential equation by separation of the variables, so let's do that. So here I have dx, and I can then integrate both sides, and I'll get that. Okay, so I can then, the left hand side of course gives me a sine inverse of y, and this is equal to x, okay, plus constant c. Okay, and so then I have that y is simply equal to sine of x plus c. Okay, c is a constant. Fine. Okay, so the subtlety over here is that given that this is non-linear differential equation, not all solutions will be of this form. Okay, if you had a linear first order differential equation, then you would be guaranteed that, okay, the solution that you have found that contains one constant, all possible solutions of that differential equation can be generated from that general solution. But this is not the case for the non-linear differential equation. So for example, going back to the differential equation, it is obvious that y is equal to plus minus 1 is a solution of this differential equation. Okay, but that is not captured by y is equal to sine of x plus c. Okay, so y is equal to, of course, plus minus 1 means that for all values of x, y is either equal to plus 1 or minus 1, but this is not going to be true for this solution. Okay, so in other words, these are known as singular solutions of the differential equation. Okay, these are not captured by the general solution, because by going back, of course, this step over here would not be valid for y is equal to plus minus 1. Okay, because then you would be dividing by 0. But thankfully most of the time we'll be dealing with linear first order differential equations, so you need not worry about any singular solutions. Okay, for linear first order differential equations, once you get the general solution, all you have to figure out is that you just figure out the values of the constant that you are from the initial conditions, and that's it. That is the solution of your differential equation. Okay, so with that in mind, let me now deal with a general linear first order differential equation. So a simple example would be, for example, an object falling down, okay, in the presence of air resistance. Okay, so if the drag force is proportional to the velocity, the object is falling down, you have mg, which is the weight of the object, okay, that's acting downwards, and then you have some force, drag force acting upwards, kv, where v is the speed of the object. Then if you apply Newton's second law, you can write mg minus kv is equal to m dv by dt. Okay, so this is a linear first order differential equation. Okay, so how do you solve a linear first order differential equation? The general form that you can write for the linear first order differential equation is this form. Okay, so p and q are functions of x, arbitrary functions of x. Okay, and what do you do then? So the general strategy in solving linear differential equations is to first of all look at the so-called homogeneous linear differential equation. That just means that the term that contains only x in your differential equation, that is 0. Okay, so the homogeneous linear differential equation associated with the above differential equation is the following. You just have that q is equal to 0. Okay, that's the key idea in linear differential equation is that the solutions of your original differential equation are closely related to the solutions of the associated homogeneous linear differential equation. So let's first try to solve this homogeneous linear differential equation. Well, solving this homogeneous linear differential equation is easy. So you can do it by separation of variables. So you bring all the y's to one side, all the x's to the other side, and you immediately have that dy by dx is equal to minus p of x y, which immediately implies that dy over y is equal to minus p of x dx, and then you integrate both sides to get that ln y is equal to minus the integral of p plus a constant, which I write in the form of ln of a. A is your constant, okay. And just for convenience purposes, I define this integral as I. Okay, of course the value of I depends on what p is. So I can rewrite this as ln y over a is equal to minus I. So in other words, y over a is equal to e raised to power minus I. So y is equal to a e raised to power minus I. Okay, right, where a is a constant. Okay, fine. But how does that help us in solving the original non-homogeneous differential equation? Okay, now the good thing about differential equations is that many times you can guess the solution. Okay, so if you can guess the solution, you can try out your guess. Just plug your guess into the original differential equation and see whether it works or not. And that's many times very easy to do, because remember, differentiating is usually easier compared to integrating. Okay, so if this is your solution for the case where you have q is equal to 0, okay, my guess would be that if q is non-zero, okay, so you can imagine that if q is very close to 0, then a is approximately a constant. Okay, right, because if q is 0, then a is certainly a constant. Okay, but if q is close to 0, then a is close to being a constant. Probably it does vary with x. Okay, so in general, I guess would be for the general linear first order differential equation, my guess is that y is equal to a, but now this a is not a constant, it's actually a function of x. Okay, e raised to power minus I. That's my guess. Okay, and then I just have to find out what this a is. Okay, for my general linear first order differential equation. So let's just plug this in. Remember, my general first order linear differential equation is this thing, p. Okay, p is a function of x. I'm just not writing it out explicitly, is equal to q. So let's just plug this in. Okay, so if this thing goes over here and this thing goes over here, what do I get? Okay, so first of all, let's work out the derivative. So the derivative immediately gives you that you first take out a, and then you differentiate e raised to power minus I. If you're going to differentiate e raised to power minus I, you'll keep e raised to power minus I as it is, but then you have minus p. Okay, because when you differentiate the exponent, you pick up a minus sign, and the derivative of I is just equal to p, because I is the integral of p. So you have minus p over here, right? And you then have, remember, you have the product rule, so you are differentiating y, so you're now keeping e raised to power minus I constant, and you are differentiating a, so you have dA by dx. Okay, that's the second term. Okay, so this is the derivative of y, and then you have plus p times y, so you have p times y, which is a of x, e raised to power minus I. P, remember, is also a function of x. Okay, and this is equal to q. Fine, no issues there. Now if you notice, you have a cancellation, a very nice cancellation. This thing is equal to that thing apart from this minus sign. Okay, so you have this minus sign. Okay, so these two terms cancel, and you immediately have that. What do you have? So just hang on. Okay, so hang on. Okay, so these two terms cancel, and you're left with e raised to power minus I dA by dx is equal to q. Okay, in other words, dA by dx is equal to q e raised to power I. Okay, so I can then solve for a. So a of x is what? Is equal to q e raised to power I, the integral. Okay, that. Okay, What is that it? So I also have a constant over here plus c. Okay, so that's what I have. Okay, fine. So now let me just plug this back in. So remember, y was equal to a e raised to power minus I, right? So this means that y must be equal to e raised to power minus I q e raised to power I dx plus c e raised to power minus I. Okay, and that's what I have. Okay, that is the solution of my first order linear differential equation. You can check this. If q is 0, then this thing goes away, of course, and you get the original solution to your homogeneous linear first order linear differential equation. So what we have learned over here is something powerful. The solution of a linear differential equation is the sum of the solution to the homogeneous linear differential equation, which you have over here. This is the solution to the homogeneous linear differential equation. This is called the complementary solution, YC, plus a solution of the non-homogeneous linear differential equation, which is the particular solution. Okay, this fact will remain true even for higher order differential equations. So over there we'll first solve the homogeneous linear differential equation and then try to find out the particular solution and just add the two. Okay, so this gives you a powerful way of analyzing linear differential equation. That's the nice thing about them, and there are many other nice things about them, as you'll see later on. Okay, so now let's use what we have learned to solve a simple linear first order differential equation. Like I mentioned before, you get a linear first order differential equation. You should try to analyze a falling object that is experiencing a drag force which is proportional to the speed of the object. So if you drop an object, well, there are two forces acting on it at an instant of time. There's a weight and there's a drag force. The drag force, I assume that it's proportional to the speed of the object. So k is your proportionality constant. I then apply Newton's second law and write that the net force acting on the object is equal to the mass times acceleration. So this is a linear first order differential equation for the speed of the object. Okay, so I can then figure the objective of course here is to find out the function v as a function of time. Okay, so you can rearrange this to this form, kv is equal to mg, right? And then this implies of course dv by dt plus k over m v is equal to g, and this is exactly the form that we had. So remember, the general linear first order differential equation that we were dealing with was of the form q. Okay, so you can, the role of y is now of course being played by v, the role of x is being played by time t. Okay, p is simply a constant which is k over m, q is a constant which is g. Okay, the solution to this, remember, was y is equal to e raised to power minus I, then you had e raised to power I q dx plus c e raised to power minus I. That's what you had. Okay, so adapting this solution to the current situation at hand, I'll be writing v of t is equal to e raised to minus I, but first I have to figure out I. For our case, I, remember, was the integral of p with respect to x. So for our situation it's k over m, because p is simply k over m, and then you have dt, right? So this is kt over m. Okay, so you get then e raised to power minus kt over m, e raised to power kt over m, and q of course is g dt, right, plus c we have to determine from the initial condition. So this is e raised to power minus kt over m. Okay, right, so this gives you g goes outside, e raised to power minus kt over m, and then you have to integrate e raised to power kt over m. Okay, so that gives you m over k and you have e raised to power kt over m, right, plus c e raised to power minus kt over m, and this is equal to mg over k plus c e raised to power minus kt over m. Okay, right. So then we just have to figure out what's c. So to figure out c, what we can do is, let me just rewrite the solution. So you have c e raised to power minus kt over m plus m g over k, right? So to figure out c, remember t is equal to 0. The speed of the object, if you drop it from rest, is going to be 0. Okay, so let's plug this in. You get 0 is equal to c plus mg over k, right? So this implies that c is equal to minus mg over k. Okay, so in other words, v of t is going to be equal to mg over k 1 minus e raised to power minus kt over. So that's what I get. Let's see whether this makes sense or not. Okay, so at t is equal to 0, of course I get 1 minus 1 in the brackets, so I get 0 for the speed. Okay, that makes sense because I assume that the object is falling from rest. Okay, as t becomes larger and larger, the object obtains a stationary value. The stationary value, of course, means that this thing approaches 0, because as t becomes infinity, the exponent becomes minus infinity, and you will get 0. So v of t approaches mg over k as t approaches infinity. So this limiting value is called the terminal velocity. Okay, this is the speed, of course, that the object obtains when it's once it has fallen down for a large amount of time. Okay, one final check that we should do is check the dimensions. Okay, so first of all, to do that, we need to find out the dimensions of k. Remember, kv is a force. Okay, so if kv is a force, then what are the dimensions of k? So this is a force, so k has dimensions of force over velocity. Okay, so this has dimensions of kg meter per second square divided by meter per second. So this has dimensions of kg, meter and meter cancel, and your kg per second, right? That's the dimension of k. And so if you look at the exponent over here, if you look at the exponent over here, this exponent, of course, has to be dimensionless. Okay, so let's check the dimensions for this now. Kt over m, the dimension of this thing is kg per second divided by kg. Okay, because m is mass. Okay, and you then have essentially that you get dimensionless, right, which is exactly what you expect. Okay, finally you have mg over k. What's the dimension of that? That should be dimensions of velocity. So that has dimensions of kg, and you have g is acceleration, so you have meter per second square divided by k, which is kg per second. So you have kg cancels, and you have meter per second, exactly what you expect. Okay, there's another way to deal with the first order differential equation. Okay, and you'll see this in many books where they talk about the integrating factor. Okay, so I thought it would be nice to cover that as well. Okay, so just to motivate it, I'll start again from your linear first order differential equation. So suppose you have equation of this form. So you have again e y is equal to q. Okay, where p is a function of x only and q is a function of x only. So this is a linear first order differential equation, and you know how to solve this. Okay, but I can play around with this. I can multiply by dx on both sides. So I will have dy plus py dx is equal to q dx. I can then rewrite this, of course, as dy plus py minus q dx. All I've done is, of course, take q dx in this equation to the left hand side. So that's what I have. Okay. Now, if you have such an equation, okay, in general, okay, any first order differential equation you can write in the form that you have some function of x and y multiplied by dx plus some function of x and y multiplied by dy. This is equal to 0. Okay. And this equation is called exact if the left hand side is an exact differential of some function of x and y. Okay, so in other words, if you can write down that the left hand side is df is equal to 0, where capital F is a function of x and y, then you can immediately solve the differential equation in the sense that you can then immediately say that f y is a constant. Okay. Let me show you how that's done essentially, but you don't know beforehand whether this thing is an exact differential of some function capital F or not. Okay, let's first of all see whether we can quickly decide whether this is the case or not. Okay, so if you have a function of two variables, then it immediately means that the differential of that will be partial of f with respect to x, keeping y constant. I'm not writing that, plus derivative with respect to y, keeping x constant, dy. Okay, right? So that's what you have, and then you have to see, then you have to compare this with your original thing that you have. Okay, so you have compare this with this and compare this with this. Okay, so what you can then write is that if this is true, then you can write down partial okay, right? Okay, now I can differentiate this equation on both sides with respect to y, and I can differentiate this equation on both sides with respect to x. Okay, what do I get then? So I'll then get that sorry, this is partial f with respect to x, partial y to x is equal to partial of a with respect to y, and partial of y, this has to be equal to partial of b with respect to x. Okay, since I'm assuming that capital X is reasonably smooth, then the cross derivatives have to be equal, which means that I must have that partial of a with respect to y is equal to partial of b with respect to x. Okay, if this condition is met in your original differential equation, this one, okay, then you are dealing with an exact differential equation. Okay, then this differential equation can be recast in terms of this thing, the df is equal to 0. Okay, where then you can find out capital F. Okay, because you know that partial of f with respect to x is equal to a, and partial of f with respect to y is equal to b. Okay, and then you can figure out capital F from there, and then you can just set that capital F is simply equal to a constant. Okay. On the other hand, if your equation is not exact, then what do you do? Okay, so let's go back to our differential equation that we were looking at, the linear first order differential equation. Okay, this equation, this technique need not apply to just linear first order differential equation. You can apply to some other differential equations as well. Okay, but let's just apply to linear differential equation. Okay, so you have plus py is equal to q, and as we saw before, this equation can be written as py minus q q dx is equal to 0. So in our case, a is simply equal to, sorry, not a. In our case, a is simply equal to py minus q, and b is simply equal to 1. Okay, so in our case, partial of a with respect to y is equal to p. Okay, right, remember p and q are only functions of x, and partial of b with respect to x is of course 0. Okay, so this is not an exact equation. Okay, but the point now is that you can always multiply your inexact differential equation by some function of x and y. Okay, in general. Okay, that's called the integrating factor. You can multiply your differential equation by this integrating factor to make it exact. Okay, you can multiply your both sides of equation by this factor. So in other words, what I'm saying is that instead of dealing with this thing, okay, you instead deal with mu dy plus mu py minus q dx is equal to 0, where mu is a function of x and y. So mu is actually, I should write mu is a function of x and y in general. It could be only a function of x, it could be only a function of y, but in general it's a function of both x and y. Okay, and if mu turns out to be only a function of x, then there's general techniques to find out this integrating factor mu. Okay, if it's only a function of y, then there are general techniques to find out this integrating factor. But in general, if it turns out it's a function of both x and y, then there's no general technique, you just have to guess it. Okay, thankfully for most cases of interest, it turns out that it's only a function of x or a function of y. Okay, so let me proceed. Okay, so let me first of all, let's go back to a general equation. Okay, so you have a xy dx plus b xy dy is equal to 0. So I'm assuming that this is not exact. So I'll then multiply this inexact with differential equation by this integrating factor mu to make it exact. So I have then okay. And now I'm saying that this new equation has to be exact. In other words, what I'm saying is that since this new equation is exact, I must have that partial with respect to y. Remember, this partial with respect to y of mu a must be equal to partial with respect to x of mu b. That's my guiding principle on how to find mu. I have to find mu such that this relation is now satisfied. Of course, I know a and b because those are given in your differential equation. Okay, now assume for the time being that mu is only a function of x, that you can find an integrating factor that turns out that it's only a function of x. Okay, then what do you do? Okay, if it's only a function of x, then of course in the left hand side of this equation you can pull mu out, because in the left hand side you're differentiating with respect to y, and I'm assuming that mu is only a function of x. Okay, so you'll get this thing. Okay, right, and this is equal to, then you apply the product rule, so you have partial v with respect to x, right, mu plus d mu by dx, no partial derivative over here because you are assuming that mu is only a function of x. Okay, v. Okay, then what do you have? You can then rearrange this equation. Okay, so you can get essentially you can divide by mu throughout, so you'll get plus d mu over dx v over mu. Okay, and then I'll multiply both sides by dx. Okay, and I'll take this thing to that side, so I have partial a with respect to y minus partial b with respect to x, right? Okay, and then dx is equal to b d mu over mu. Okay, so and then I will then have that I can of course bring b to the other side, so I have d mu over mu is equal to 1 over b partial a with respect to y minus partial b with respect to x dx. Okay, so that's what I have. Then I need to figure out mu, and if I'll just integrate both sides, so I'll have ln of mu is equal to this thing. Okay, is equal to integral of okay. So just to clean up the notation, I'll define this as f of x. So then I can write this as okay. Notice that I'm making a subtle assumption over here that this thing, okay, this f of x is only a function of x. Okay, so that is exactly what I was assuming in the beginning, that mu is only a function of x. So I need this thing to only be a function of x, otherwise mu is not going to be a function of x alone. Okay, so that's my hope, that when I calculate this thing f of x, it turns out that it's really only a function of x, because remember a is in turn, a of course is a function of x and y in general, and b is a function of x and y as well. So it might turn out that when I do this whole calculation, f of x may not be a function of x alone, it can also depend on y. Okay, and then I have to go back. Okay, so my initial assumption then turns out to be not justified, so that mu is not a function of x alone. Okay, but let's see. Okay, so the differential equation that we are dealing with, let's see what happens over there. So I then have, of course, that mu is simply equal to e raised to power f of x dx, where my f of x I have defined as 1 over b partial of a with respect to y minus partial of b with respect to x. Okay, that's what I have. Now going back to my differential equation, linear first order differential equation, I had dy by dx plus py is equal to q, and of course I rearrange this as dy plus py minus q dx is equal to 0. So in my case, my a is equal to py minus q, and b is simply equal to 1. Okay, so for my case, f of x, fingers crossed that this is only a function of x, is just equal to 1 over 1, because b is 1. Partial of a with respect to y is simply p, right, and minus partial of b with respect to x is 0. Okay, so this is just equal to p of x. Okay, because p is only a function of x. So yeah, for our case, for a linear first order differential equation, it turns out that this function f of x is all indeed a function of x, and therefore the integrating factor mu is simply e raised to power integral of p of x dx. Okay, but this, recalling a previous notation that we defined, is simply e raised to power I. Okay, so in other words, the integrating factor that we want is simply e raised to power I. Now let's go back to our original equation. So I'll just multiply the original equation, this one, by e raised to power I on both sides, and then I know that it's then going to be an exact differential equation. So I'll get e raised to power I dy plus e raised to power I py minus q dx is equal to 0. Okay, and then I can say, okay, that this is an exact differential equation, so this is also equal to, for some function of x and y, capital F, this is also equal to this thing. Okay, so then I have to figure out capital F. Now I can just match the coefficients of dx and dy. Okay, so I have from this equation that partial of f with respect to x is equal to e raised to power I py minus q, and partial of f with respect to y is simply equal to e raised to power I. Okay. What then? So remember that I have over here on the left hand side a derivative with respect to y. Okay. The right hand side on the other hand is only a function of x. Okay. So if I solve this equation, then I can write that f of x y is simply equal to y e raised to power I plus some function only of x. Okay. I can check back. If I take the partial derivative of this f with respect to y, I get back e raised to power I. Okay. Now I have to figure out, of course, g of x, but that's easy. Okay, I can find out g of x such that partial of f with respect to x is equal to this thing. Okay, so let's do that. Partial of f with respect to x will be equal to, well, y I'm keeping as a constant, e raised to power I remains as it is, and then you have to differentiate the exponent, so you get p plus dg by dx. Okay, and this of course is nothing but e raised to power I p y minus q e raised to power I. Okay, right? So from this I can immediately figure out that dg by dx is nothing but minus q e raised to power I. So this implies that g of x is equal to minus q e raised to power I dx plus a constant. Okay, which I don't need, okay, because I'll be setting capital F equal to constant anyway. Okay, so you don't really need this. Okay, so essentially what we have then is that f of x y is equal to y e raised to power I minus q e raised to power I, right, dx, and this thing is equal to a constant, because we know that this thing, going back, that this thing is equal to d capital F, and that in turn is equal to 0, remember? Okay, so that just means that capital F has to be equal to constant, such that this differential is equal to 0. Okay, so then I can just bring this thing to that side, and I have that y e raised to power I is equal to c plus q e raised to power I dx. So in other words, y is equal to c e raised to power minus I plus e raised to power minus I q e raised to power I dx. Exactly the same as before. Okay, and again, remember you have one constant that you need to figure out, because it's a linear first order differential equation.